sub-panel can be used to increase the electrical capacity of a residence without needing a major service upgrade. By adding a sub-panel, it's possible to accommodate additional circuits and appliances without overloading the existing panel. A sub-panel allows for the separation of circuits dedicated to specific areas or systems, such as heavy-duty appliances, entertainment systems, and emergency lighting. This improves safety and reduces the risk of electrical failures. Sub-panels can be installed in remote locations, such as garages, workshops, or additions. This allows for easy access to electrical power in these areas without running long wires from the main panel. Sub-panels are typically located closer to the areas they serve, making it more convenient to access circuit breakers and perform any necessary maintenance. As an example, a sub-panel can be added to accommodate additional appliances in a kitchen, such as a new oven, dishwasher, or refrigerator. A sub-panel can also provide dedicated circuits for power tools, welding equipment, and lighting in a workshop. High-power appliances like air conditioners or electric vehicles can be placed on a separate sub-panel to avoid overloading the main panel. Sub-panels are typically more cost-effective than a major service upgrade. Sub-panels provide easier access to circuits and maintenance. Safety is improved by separating circuits and reducing overloading risks. Electrical capacity can be expanded as needed without major renovations when utilizing sub-panels. To elaborate further on the practical applications of sub-panels in residential settings, let's delve into specific scenarios and technical considerations. Firstly, consider a home renovation project where an existing kitchen is being expanded. The original electrical panel might have been sufficient for the initial kitchen setup, but with the addition of new, energy-intensive appliances like a wine cooler, a larger microwave, or a professional-grade oven, the existing circuits could become overloaded. Instead of upgrading the entire service, a sub-panel can be installed specifically to handle the increased load of the kitchen appliances. This sub-panel can be fed from the main panel with appropriately sized conductors and a circuit breaker, and then distribute power to individual circuits dedicated to each appliance. Secondly, imagine a homeowner who decides to build a detached garage or workshop. This new structure will likely require its own set of electrical needs, including lighting, power outlets for tools, and potentially even a dedicated circuit for a welder or air compressor. Running multiple circuits from the main panel in the house to the garage could be cumbersome and expensive. A more practical solution is to install a sub-panel in the garage. The sub-panel can be fed by a single, appropriately sized feeder cable from the main panel, and then distribute power to the various circuits within the garage. This simplifies the wiring and provides a central point of control for the garage's electrical system. Thirdly, consider a situation where a homeowner wants to install a backup generator to provide power during outages. A transfer switch is required to safely switch between the utility power and the generator power. A sub-panel can be used in conjunction with the transfer switch to create a dedicated circuit for essential loads that the generator will power, such as refrigerators, freezers, and critical lighting. This allows the homeowner to selectively power essential appliances during an outage without overloading the generator. Furthermore, sub-panels can be strategically used to isolate sensitive electronic equipment from electrical noise and interference. For example, a home theater system with expensive audio and video components can benefit from being powered by a dedicated sub-panel with its own grounding system. This can help to reduce hum, buzz, and other unwanted noise that can degrade the performance of the equipment. The electrical code provides specific guidelines for the installation and wiring of sub-panels to ensure safety and compliance. Some key considerations include: firstly, the feeder conductors that supply the sub-panel must be sized appropriately for the load they will carry, and they must be protected by an overcurrent device, circuit breaker, or fuse at the main panel. Secondly, the sub-panel must have a separate grounding and neutral bus bar. The grounding bus bar is connected to the grounding electrode system, which typically consists of ground rods or a connection to the metal water pipe. The neutral bus bar is only connected to the neutral conductors of the circuits served by the sub-panel. Thirdly, the neutral and grounding bus bars in the sub-panel must not be bonded together. This is a critical safety requirement that prevents neutral current from flowing through the grounding system, which could create a shock hazard. Fourthly, all circuits originating from the sub-panel must be properly grounded and protected by overcurrent devices. The size of the circuit breakers or fuses must be matched to the ampacity of the conductors they protect. Fifthly, the sub-panel must be installed in a location that is readily accessible and protected from physical damage. It should also be properly labeled to indicate its purpose and the circuits it serves. When sizing the feeder conductors and overcurrent protection for a sub-panel, it's important to perform a load calculation to determine the total demand load that the sub-panel will be expected to carry. The electrical code provides methods for calculating the demand load of various types of circuits and appliances. For example, the demand load for general lighting circuits is typically calculated at 3 volt-amps per square foot of floor area. The demand load for appliance circuits is calculated based on the rating of the appliances. The electrical code also allows for demand factors to be applied to certain types of loads, which can reduce the size of the feeder conductors and overcurrent protection required. For example, a demand factor of 75% can be applied to the total demand load of 4 or more appliances connected to a sub-panel. It's also important to consider the voltage drop in the feeder conductors when sizing them. Voltage drop occurs when the voltage of the load is less than the voltage of the source due to the resistance of the conductors. The electrical code recommends that the voltage drop in the feeder conductors should not exceed 3% for power, heating, and lighting circuits. The voltage drop can be calculated using Ohm's law and the resistance of the conductors. If the voltage drop is excessive, the size of the feeder conductors must be increased to reduce the resistance. In addition to the electrical code requirements, there are also best practices that should be followed when installing a sub-panel. Firstly, use high-quality materials and components. This will help to ensure the reliability and longevity of the installation. Secondly, carefully plan the layout of the sub-panel and the circuits it will serve. This will make it easier to install and maintain the system. Thirdly, properly label all circuits and components. This will help to prevent confusion and errors in the future. Fourthly, test the installation thoroughly after it is completed. This will help to identify any problems and ensure that the system is operating safely and correctly. For specific conductor sizing, refer to NEC Table 310.15b16 for ampacities of insulated conductors rated up to 600 volts based on temperature rating and insulation type. This table helps determine the appropriate wire gauge for a given amperage. For example, a 60-amp circuit might require 6 American wire gauge copper conductors, assuming a 75°C temperature rating. For overcurrent protection, NEC Section 240.4b addresses situations where the conductor ampacity doesn't match a standard overcurrent device size. It allows the next higher standard overcurrent device rating to be used, provided certain conditions are met, such as the conductor being part of a multi-outlet branch circuit. Grounding requirements are detailed in NEC Article 250. It specifies the methods for grounding and bonding electrical systems to ensure a low impedance path for fault current. This includes proper grounding electrode systems and bonding of metal enclosures. When installing a sub-panel in a residential setting, adherence to NEC Article 408, which covers switchboards and panel boards, is essential. This article provides requirements for the construction, installation, and overcurrent protection of panel boards. It includes guidelines on conductor termination, busbar arrangements, and enclosure specifications. Article 312 provides guidelines on installing cabinets, cut-out boxes, and meter socket enclosures in wet or damp locations, which is crucial for outdoor sub-panel installations or areas prone to moisture. It specifies requirements for weatherproof enclosures, drainage, and corrosion protection. For sub-panels feeding sensitive electronic equipment, NEC Section 647.7 specifies requirements for sensitive electronic equipment grounding and bonding. It ensures that the grounding system minimizes electrical noise and interference. NEC Article 110 provides general requirements for electrical installations, including workmanship, equipment labeling, and access to electrical equipment. It emphasizes the importance of proper installation techniques and adherence to manufacturer's instructions. Considering these factors, installing a sub-panel can be a practical and cost-effective solution for expanding electrical capacity, separating circuits, providing power to remote locations, and improving convenience and safety in a residential setting. When planning the installation of a sub-panel, it is essential to perform a thorough load calculation to determine the required capacity. This calculation involves adding up the anticipated loads of all the circuits that will be connected to the sub-panel. It's also crucial to factor in any future expansion plans to avoid the need for another upgrade later on. The electrical code provides guidelines for calculating the load of different types of circuits, such as lighting, receptacles, and appliances. For example, the general lighting load is typically calculated based on the square footage of the area served by the circuit. Receptacle circuits are calculated based on a minimum load per receptacle outlet. Appliance circuits are calculated based on the nameplate rating of the appliance. In addition to the general lighting, receptacle, and appliance loads, it's also important to consider any larger or specialized loads that will be connected to the sub-panel, such as electric vehicle chargers, welders, or air conditioners. These loads may require dedicated circuits and may have a significant impact on the overall load calculation. Once the load calculation is complete, it's possible to determine the required amperage rating of the sub-panel and the size of the feeder conductors that will supply it. The feeder conductors must be sized to carry the total load of the sub-panel, plus any applicable demand factors. Demand factors are reductions in the calculated load that are allowed by the electrical code based on the assumption that not all of the connected loads will be operating at the same time. For example, a demand factor of 75% may be applied to the total load of 4 or more household appliances that are connected to the sub-panel. The electrical code also specifies the minimum size of the grounding electrode conductor that must be connected to the sub-panel. The grounding electrode conductor provides a path for fault current to flow back to the source, which helps to protect against electric shock. When selecting a location for the sub-panel, it's important to consider factors such as accessibility, convenience, and safety. The sub-panel should be located in an area that is easily accessible for maintenance and repairs. It should also be located in a dry and well-ventilated area to prevent corrosion and overheating. Additionally, the sub-panel should be located away from flammable materials and other hazards. When installing the sub-panel, it's important to follow all applicable electrical codes and regulations. This includes ensuring that all wiring is properly installed and grounded, and that all connections are tight and secure. It's also important to label all circuits and components to make it easier to identify and troubleshoot problems in the future. Once the sub-panel is installed, it's important to test it thoroughly to ensure that it is operating correctly. This includes checking the voltage and current on all circuits, and verifying that all safety devices are functioning properly. It's also important to document the installation, including the load calculation, the wiring diagram, and the test results. This documentation will be helpful for future maintenance and repairs. In summary, installing a sub-panel can be a practical and cost-effective way to expand the electrical capacity of a residential property. By following the guidelines and recommendations outlined above, it's possible to ensure that the sub-panel is installed safely and correctly, and that it will provide reliable power for years to come. Proper planning, load calculation, and adherence to electrical codes are essential for a successful sub-panel installation.